Chang, coming to you for our BC class, lesson 2, second lesson of the year, 2021-2022 school year. In this lesson, we will look at three main things, three main objectives. The first is to revisit what's called the Squeeze Theorem. The second objective is to deal with limits involving infinity, whether you're evaluating the limits as x approaches infinity or negative infinity, or perhaps the answer or the limit itself ends up as positive or negative infinity. And the third objective is to kind of sum it up, okay, the things that we learned today, as well as the things that we have been dealing with, okay. So that will be the additional practice, and this one will be your practice assignment for lesson 2, whatever we do not cover in here. All right, so let's get right to it. We'll start with this idea, this theorem called the Squeeze Theorem. It's also called the sandwich theorem or the pinching theorem. I got this one from our own textbook. Here you could start with this figures 2.7 to get an idea of this. I'm sure you've learned this last year, but again, if this is the first time, that's okay. It's pretty intuitive. So we're concerned with the limit of the function f. Okay, function f as x approaches c from either side, and in this one, okay, you could see that function f is in between. It's wedged in between function h and function g at every single x value, but they happen to converge as x approaches c. And in that instance, because the limit of the function h and the limit of the function g as x approaches c is both L, and because function f is sandwiched in between function h and function g, by the Squeeze theorem, function f's limit has to be L as well as x approaches c. The formal notations, again, formal description of the Squeeze theorem right here, as you can see, if the limit of the g of x as x approaches c and the limit of the h of x as x approaches c is equal to L, and then we know that f of x is in between g of x and h of x for all x, then you could see that the limit of the f of x has to be L as well. Okay, so as an example, let's take a look at example number 9 right here. Okay, this is more applicable, I think, okay, because again, the direct substitution wouldn't work here. If you were to substitute 0 for x, much less the sign of 1 over 0, okay, 1 over 0 again fails, okay, with the direct substitution method. And besides, sign of 1 over 0 is not defined either. But however, we could use the idea that when we graph sine of 1 over x, that would be the blue graph right here that you see. Let me see. Yeah, that's it right there. And then you could see that it's in between, it's sandwiched in between these two other functions, okay, these two symmetric functions, one being the positive x squared, it's just a parabola that opens up, and then the other one being negative x squared. Okay, so we will be using that to evaluate. Okay, I'm sorry, this is the graph. The blue one is the graph of the x squared times the sine of 1 over x. And then you can see that it's in between, it's sandwiched in between positive x squared and negative x squared for all x. Once again, for this particular function, we don't have a defined value as x approaches 0. I guess graphically we could see where we end up. Okay, but let's apply the Squeeze theorem for this one. So how do we so here's are the steps, okay, to apply the Squeeze theorem. We start with the idea that even though we can't find the limit of sine of 1 over x as x approaches 0, we know that for any sine functions or cosine functions, okay, your output would have to be in between -1 and 1. And then I could illustrate this with decimals right here. Sine of 1 over x, as you could see, okay, no matter what the x value is, you could see that the y value, the output, has to be in between -1 and +1, even as x approaches 0 right there. Okay, so using that fact, and also we're concerned with x squared times the sine of 1 over x. So with the inequality that I started with, okay, so we know that this is true. And then the next step, then by multiplying everything by x squared, we would end up with negative x squared is less than or equal to x squared times the sine of 1 over x, which is then less than or equal to positive x squared. Okay, we know that x squared is a positive value anyway, so we don't have to worry about reversing the inequality symbol. Even so, you could just rearrange things and you would still have x squared times sine of 1 over x in the middle anyway. So we have this, negative x squared is less than or equal to x squared times the sine of 1 over x, which is less than or equal to x squared. And this statement right here, this inequality, this compound inequality is described already in this picture, in this graph right here. So now now I'm going to use limits. I'm going to add limits to that, limit notations to this, and you're allowed to do this. This is one of the theorems not covered in our textbook, but it is covered in another textbook that I use. So even if I were to introduce the limit notation for each part of this inequality, it will still hold true. Okay, so as you can see, limit of the negative x squared would have to be less than or equal to what we're trying to solve for, and which would then be less than or equal to limit of the x squared as x approaches 0 for all of them. And it's pretty straightforward from there, right? Limit of the negative x squared as x approaches 0 would be 0, as indicated by the graph, and algebraically as well. Limit of the positive x squared is also 0, right? As x approaches 0. And the one that we're looking for is in between 0 and 0. Right there. Okay, so this is where the squeeze theorem comes into play. Then we could conclude that limit of the x squared times the sine of 1 over x, because it's in between 0 and 0, sandwiched in between these two functions, is indeed 0. Okay, by the squeeze theorem. And then we'll look at one more example after this for this. Example. So we're given the function f of x. We're not told what exactly f of x represents, but we're told that it's a function that's in between 4x minus 9 and x squared minus 4x plus 7. Okay, less than or equal to x squared minus 4x plus 7, but at the same time greater than or equal to 4x minus 9 for all x. Right there. And then somehow we're supposed to find the limit of that function, that particular unknown function, as x approaches 4. Okay, so graphically speaking, okay, so here are the two graphs, at least one that is greater than f of x, greater than or equal to f of x, and one that's less than or equal to f of x. Notice that they converge as x approaches 4, and that probably has to do with the answer. Okay, so but how do we formalize this? How do we justify that the limit of the function as x approaches 4 is indeed 7? Okay, so for this one, all we have to do is to introduce the limit notation for each part of that compound inequality. Okay, this right now, this step is not the application of the squeeze theorem yet. Okay, this is another theorem that allows you to. So if you have an inequality, then you could introduce the limits with the x approaching the same value. That's okay. You're maintaining that inequality. Okay, so let me just make sure, double check that I wrote everything correctly. And what do we know about this one? We could look at the graph, or we could just algebraically see that it's going to be 16 minus 9, which is 7. On the other hand, we got the 4 squared minus 4x plus 7, which is also 7. So as you could see, so limit of f of x as x approaches 4 must be in between 7 and 7. So now here you could formalize this by saying that by the squeeze theorem, and by prior steps right here, limits of the f of x as x approaches 4 must be 7 right there. Okay, that's it. So that right there is the application of the squeeze theorem. I believe we have a few more practice problems back here, okay, or second page. Okay, so I'll get to example 2 as well. Let's see. The only thing different about this is that now we're involving the limit of a function as x approaches to positive infinity or negative infinity. In this case, it's positive infinity. I think we discussed some of the blocks. Okay, I might have covered this already. Okay, so we know what the answer is. Over time, sine of x over x will become 0. Okay, or will approach 0 as x approaches positive infinity. But let's try to justify this using the squeeze theorem again. Okay, so rather than starting right away with the sine of x over x, we start with this idea that sine of x is always in between these two numbers. Sine of x would be in between -1 and 1. And from there, I'm concerned with the function that is defined as sine of x over x. So what I could do is I could divide by x to every part of this inequality. Okay, dividing by x to left side, dividing by x to the right side. But the inequality still holds true. Okay. And then I could introduce the limit notation for each part. Limit as x approaches infinity of -1 over x is less than or equal to the limit as x approaches positive infinity of the sine of x over x, which is less than or equal to limit as x approaches infinity of the 1 over x. And by now you should know this. Okay, limit of the 1 over x as x approaches infinity would be 0. And likewise, limit of the negative 1 over x as x approaches infinity would be 0 as well. So once again, just like the previous two examples, okay, the limit of sine of x over x is sandwiched in between 0 and 0. Okay, so once again, by the Squeeze theorem, you could say that limit of this is equal to 0 right there. And then again, you could verify that graphically, and you could verify that numerically by using a table. That's fine too. Let's take a look at number 10. Okay, this is from our own textbook. Number 10, by using the Squeeze theorem, we are asked to evaluate the limit of the 1 minus cosine of x over x squared as the x approaches to negative infinity. Okay, you got a couple options here. You could split up this problem into two fractions if you wish to, and then evaluate both. Okay, 1 over x squared minus the cosine of x over x squared, or you could just deal with the fact that 1 minus the cosine of x, which is the same thing as negative cosine of x plus 1, would be in between, not -1 and 1 in this case, right? Because you have a cosine function or the inverted cosine function, and you're adding 1 to the max and min. So instead of -1 and 1, you end up having 0 and 2. Okay, so 0 is less than or equal to negative cosine of x plus 1, which is less than or equal to 2. And then I want to get to the intended function, 1 minus cosine of x over x squared. So I'm going to divide everything by x squared. Divide each part by x squared. And then I could introduce the limit notation for each. As x approaches negative infinity in this case, which is less than or equal to limit as x approaches negative infinity of the 1 minus cosine of x over x squared, which is less than or equal to limits as x approaches negative infinity of 2 over x squared. My fingers are crossed that I'm hoping that the left limit is equal to the right limit, so I could conclude that the middle limit must be the same as well. Let's see. Okay, limit of the 0 over x squared as x approaches negative infinity. Okay, you could think about negative 10,000, negative 100,000, negative 1 million. It doesn't matter. The whole thing will converge to 0. And then likewise, 2 over x squared. Okay, the denominator will get larger and larger, increasingly larger. The numerator is meaningless, insignificant. Okay, so the whole thing will converge to 0. You could take a look at it graphically too if you're not sure. And as a result, we could conclude that the middle part is 0 by the squeeze theorem. Okay, there you have it. So that's it. That's number 10. I want you to try 9, 10, and 9, 11, and 12 in a similar, in the similar manner. All right, let's go to another application. Okay, that was shown from our textbook, lesson 2.2 from our textbook. If you're wondering, it's at the end, and it's not a critical, it's not a vital application or concept, but it could be practical. Okay, once you get the hang of it, okay, you might find some occasions to apply this one. But again, it's not absolutely necessary. There's other ways to evaluate these forms of limits without having to resort to this application. But nonetheless, okay, so here's the concept, or here's the application. As I will illustrate graphically, and think about it a little more numerically too. A limit of the function, any function of x, okay, limit of the function of x, if you have to evaluate that with x approaching 0 from the right side, so x approaching 0 from the right side, would be equivalent to the limit of the f for the reciprocal of x, 1 over x. You would also have to change this one as x approaches to positive infinity. Again, there's some similarities there. Okay, and take a look at the next statement. It will be just a negative version of that. Okay, the almost you could say inverted version of that. Limit of the f of x as x approaches 0 from the left side this time would be equivalent to the limits of the f for the reciprocal of x, f of 1 over x, as x approaches negative infinity. It exactly mirrors the first statement. Okay, so let's see what either of these two statements are, again, should look graphically. So let me erase my original graph right here. Okay, take a look at this simple function right here, cosine of x. So we're pretending that f of x is equal to cosine of x, and suppose that you were concerned with the limit of this function as x approaches 0 from the right side, I should say, and clearly the answer will be 1. The left side doesn't matter; the answer will be 1 regardless. But now I want to compare this with the same function, which is cosine, but the argument would be the reciprocal of x, which would be 1 over x. And let me see, I should use a different color for this one. Oh, it's not allowing me to use a different color, so let me erase the first graph. Okay, so here's cosine of 1 over x. This time, okay, go back to your equivalency statements right there. So limit of the f of x as x approaches 0 from the right side, according to this statement, is equivalent to the limit of the f of the reciprocal of x as x approaches to positive infinity. So is that the case as you look at this graph? Okay, so as you approach positive infinity, looks like there's not going to be any change. You could see that the y value is 1, okay, or very, very close to 1. Okay. All right, you can see that right there. Okay, and then the left side is true as well. Okay, if you approach, okay, so if you're looking at this function, and then if you're evaluating the limit of this as x approaches negative infinity, okay, you can see that it's also 1. Now go back to the original function. Okay, so that was the same value for the limit as x approaches 0 from the right side as well as the left side. Okay, so graphically you can see that. Okay, conceptually you can see that as well. Let me write that statement, the specific function statement right here. So the limit of the cosine of x as x approaches 0 from the right side is equal to the limit of the cosine for the reciprocal of x as x approaches positive infinity. And likewise, or similarly, limit for cosine of x as x approaching 0 from the left side would then be equivalent to the limit for cosine of 1 over x as x approaches negative infinity, as was the case graphically. And again, numerically, you could think about this, okay? You could think about an x value that's getting closer and closer to 0 from the right side, okay? And then you could think about this, okay? What happens if you have an increasingly larger and larger and larger value for x? What's 1 over x right there? Okay, and then what happens to the limit of the cosine of that, right? Or what happens to the cosine of that value, that particular value? So numerically or conceptually, you could think about that too. One quick example right here, example 9 right there. Find limit of the 1 over sine of x as x approaches positive infinity without having to graph this exact function. So a way to apply what we just talked about would be to tweak this problem into sine of x, right? Because x would be the reciprocal for 1 over x this time. And then I could write that as limit, since I'm dealing with positive infinity for the original statement. Now I'm going to use a tweaked version of that limit statement. Okay, so it will be equivalent to, these two things will be the same. So it will be the limit of the sine of x as x approaches 0 from the right side. And right side, left side or right side doesn't matter for this one. Sine of 0 would still be 0. Okay, so the answer to this one would be 0 as well. Sine of 1 over x as x gets larger and larger would converge to 0. Okay, let me see, what do we have? Let's take a look at one more here. 49. So I'm take a look at 49 right there. So without having to graph the original function f of x, okay, we're going to use the graph of the f of the reciprocal. So how do I do that? Okay, so limit of the f of x as x approaches to positive infinity would then be equal to the limit of the f of the 1 over x as x approaches 0 from the right side. So maybe I should put a plus sign to emphasize that this is positive infinity. What are we dealing with here? Let's see. So that what that means is that limit of the x times e to the x as x approaches to positive infinity would have to equal the limit of the, instead of the x, variable x, or the argument x, we have 1 over x. And instead of e to the x, I have e to the 1 over x, or e to the negative x. But then I would have to change where x is approaching 2. So this would be 0 from the right side. So your task after that would be to graph this one instead of graphing the original function, because that would be too easy. So you will graph this one, and then you would take a look at, you would evaluate that limit by using the x values that are approaching 0 from the right side, okay, or using the trend of the graph right there. So I hope you can then do the same thing for 50, 51, and 52, and the second half of 49 as well. So that will be part of your practice. All right, so here is the last page. This is your last task. So what I want you to do this week for your practice, so along with this last page, I just want to double check. Okay, I want you to finish these 3 problems, 50, 51, and 52 from the third page. And from your second page, it was, okay, where we had numbers 9, 10, 11, and 12. I've shown you how to approach something like this with number 10, using number 10 as an example. So on this one, we are pretty much summing it up, okay, everything that we have so far. And perhaps some of these examples are beyond, okay, or before this lesson. Part A, for instance, we've seen something like this one in our last practice. Part C and D, no algebraic manipulation per se. You could write the answers for those conceptually. That's fine. Okay, likewise for E. For G, my hint would be, I think you could see it. Okay, so you could use a L'Hopital's rule. I'm sorry, you could use a Squeeze theorem, and I think L'Hopital's rule might work for that one. Is it an infinity over infinity indeterminate case? You could try that, okay, to see if that works or not. Okay, so part H, you could try that one. algebraically as well. If not, okay, at least take a look at it graphically. And I'm mainly concerned with parts B and F. Okay, I'll show you how to algebraically evaluate or manipulate to arrive at the limit value of this particular function or expression. So even though this is not a rational function to begin with, you could make it look like a rational function by writing it over 1. And then you could still multiply by the conjugates of the numerator, difficult for me to say, to rationalize exactly that. Okay, so in doing so, let's see what happens. Okay, so you got the radical x squared plus 1 multiplied by itself, which is x squared plus 1. You got the outer you got the outer product and the inner product. They will cancel each other out, and you got the outer products right there. Okay, you got the negative x times x, which will give you negative x squared, all over radical x squared plus 1 plus x. And again, I keep reminding myself that this is a limit question. I have to write the limit notation at the front. So it's already pretty nice. Okay, the x squares will cancel out, and you're left with the limit as x approaches infinity of 1 over radical x squared plus 1 plus x. And then some of you might, okay, especially if this is a multiple choice question, I think you could stop there, right? You see that, oh, I know that the square root of x squared plus 1 as x approaches infinity would simply be a larger and larger increasing value. Same thing likewise with the x portion plus x, right? That will be larger and larger. So in the end, you're dealing with 1 over infinity nonetheless. Okay, so your answer appears to be 0. You could also think of it this way too. Okay, the square root of x squared plus 1 over the long run, because the x squared value is so much greater than the plus 1 portion, that the plus 1 part becomes again insignificant or meaningless right there. So you're essentially dealing with the square root of x squared anyway. Okay, but again, if you're not satisfied yet with what we have so far, you could do more algebraically. Okay, I mean, you will rarely do this, but there's this technique that if you're dealing with the square root of x squared, okay, or the square root of x squared plus anything on the denominator, you may divide both the numerator and the denominator by x. And in doing so, you have the limit of the 1 over x all over the square root of x squared plus 1 over x plus the x over x, which is 1, and then you could rewrite that as 1 over x doesn't change. The square root of x squared plus 1 over x, I could rewrite that as the square root of x squared plus 1 divided by x is the same thing as the square root of x squared, as we know, and there's a reason why I'm rewriting x as the square root of x squared. And then I could then rewrite that as, I could combine these square roots, the quotient of the two square roots right there, as the square root of x squared plus 1 all over x squared, and then there's a plus 1 still on the outside, and then it's getting pretty messy here. So limits as x approaches infinity of the 1 over x all over, so we got the square root of x squared plus 1 over x squared. I could rewrite that again as we got x squared over x squared plus the 1 over x squared. I could split that up into two fractions inside the radical, and the reason why I want to do that is to rewrite the inner content of the radical again as 1 plus 1 over x squared. And then again, I'm taking the limit of this as x is approaching positive infinity. And as you can see that this would be 0 then in that case. Inside we have the 1 over x squared. That would be 0. So you're essentially left with 1 over the square root of 1 plus 1. I'm sorry, 0 over the square root of 1 plus 1, which would then be 0 right there. Okay, so again, a lot of steps to arrive to that, okay, but this is as algebraic as you could get, okay, with this special example, with this unique example. You could try f in the same manner, okay, to see if that works. Okay, if not, we could discuss it during this week as well. So good luck with everything. Please do the best you can today. Finish as much as you can today, and then I'll see you next time.